Well, I mean, the fact that he's doing a surface nucleation and he's using a volumetric free energy, that's kind of a problem. I didn't really bring that up, but that seems to be a pretty major problem with how he's going at it. But otherwise, it isn't. Otherwise, there isn't. Is there anything else in that homework? I mean, it was just kind of the rest of it was like essay.
There's something that they said that
Oh, this is the wrong thing.
7. And maybe I could have said something to do with safety methods.
Yeah, so it should have been kind of straightforward, I guess. Anyway, I haven't looked at them yet. I guess I'll go through that on Thursday. Anyway, I think we're done. Usually I spend 2 weeks on surfaces, but I guess I'm not. I seem to have finished that. So I'm up to this thing. This entity of formation, which is it's mostly metallurgy stuff. And actually it's so the homework this week on that is about it's a recycled one, but it's on this MOFS. Not this. There's a bunch of MOFS papers here. Heat of formation for perovskite, heat of formation for MOFS.
That's metal organic framework.
Yeah, yeah. So anyway, in it mostly these things are like anyway. So it should be okay. Like this. This is like pretty much about the heat of formation stuff. Let's see. So let me get back to this. Anyway, I'm just going to kind of go through this thing, I guess. So anyway, this is kind of review. It depends what your background is, whether this is review or not. But so you talk about like, so you have to be relative to something. So you talk about the relative to like the ground state of things. So whatever the natural state is at room temperature and atmospheric pressure, you say like N2O2. So like carbon and graphite form, heat of formation 0. So you just define it. Like so anything oxygen, which would be O2, it's just like 0. Right? Hydrogen H2 0, nitrogen N2 0, and then all these gases and they're in the kind of the natural state at room temperature is 0 for the. So if you want to know the enthalpy at some temperature, then you need the heat capacity. So you go, I mean, you take this and then you integrate the heat capacity dt, Cp dt, and so this is like this typical table, but you can get this from the NIST chemistry web book, and you can also get it from basically any book, or you can get it from Googling it, or you can get it basically a lot of places. This kind of power series and temperature. The heat capacity isn't just a value, it changes with temperature. It's just like a power series. This value plus that times T plus that times T. So if you integrate that over T, then you end up with T times this for the integral that adds to delta H. Then it's T squared T squared divided by 2, right? Times this, and then T cubed divided by 3 times this to get the value that you add with the delta H at 0 to get whatever the enthalpy is wherever you are, right? And then the free energy is kind of like the difference between these two is the entropy. Delta S, right? So delta S times T. So anyway, so you can, this also has the entropy in it then to this table, right? So all these things are negative except for this because these things are that form like they're stable compounds that form. So it has to be a negative free energy. And free energy has to drop or it wouldn't be stable. So if it's stable, then it's gonna have a negative free energy, right? Negative enthalpy. So and then you use kind of Hess's law to get whatever you want. Kind of had this lingering 2 week long kind of congestion, so I'm bringing a mask around with me, but so far I haven't worn it. I'm not sure it doesn't seem to be deadly, whatever I have, but definitely have a lingering thing. Anyway, so that's kind of the picture of the heat of formation, and then the chapter mostly goes through like, all right, so this thing is one thing that comes up. So where this, I think this is in the book, but then this is from a paper that I used to work with these guys in ETH, this Wendell Stark and some other people, Pratt Sanis is there. They do this business, they burn things. They burn and make a ceramic oxide usually. But then Wendell started making ground state metals that way. So you make nanoparticles. There's a high temperature, it's like 2000-degree flame, and then you quench it. So you basically get a deep quench and you form nanoparticles that way. So you can make like bags of nanoparticles in a lab this way. Like you just burn it, torch it up. So the original would be like silica. So you start with either an organosilane like silicon tetraethoxy. It's usually an oxygen and some organic group like methyl, ethyl, butyl. So this TiOS would be tetraethyl orthosilicate, and then TMOS is tetramethyl orthosilicate. So Si has four, coordination 4, and it's got O, carbon on the end. The carbon and the oxygen are the fuel, more or less. You can add other fuel and then you just burn it, and then you get nanoparticles from that if you want. I mean, it's fumed silica. You can make, that's how most titanium is made too, for paint and things. Anyway, here they're making ground state metal, so they need this thing called an Ellingham diagram, which is, it's a way to plot out. So you want to, so you're going to have like reduction. So you remove the oxygen from the oxide. So you make a metal, ground state metal, or you're going to make an oxide. And depending on where you are on this Ellingham diagram, then you can figure out the region where you're going to make the, usually you want to make a ground state metal, like that's the target. Like you want to take iron oxide and turn it into iron to make steel or something, right? So basically you have this diagram that's going to tell you, and when you do that, you're going to use like carbon to reduce usually use like coke to reduce this iron oxide. So the question is like, what temperature do you need to go to do that, right? So any kind of, you're dealing with an ore and you want to turn it into a metal, you need this Ellingham diagram. And in this case, the reducing agent is hydrogen. So hydrogen is reducing these metals to get ground state metal. And then it would be an oxide if it's in this region. And then depending on the concentration of hydrogen and then the temperature, you can find a region where you can make the ground state metal. So this all depends on this heats of formation. That's why it's in this heat of formation thing. So like heat of formation of, well, nitrous positive because it's not stable. It's like when you have a big coal plant, you're making NOx, none of those are stable, but they're being made because you're at such a high temperature. So you're like in the Ellingham diagram, you can oxidize the you're in a region of really high temperature, you can oxidize the nitrogen with something like the carbon that's in the coal that's going in through the plant, through a coal plant. And that's how you make like nitrous oxides and nitrous oxides aren't stable. You can produce large amounts of them in a coal plant, and then you need to somehow get rid of that. So to get rid of that, you put in, basically they put in ammonia, reacts with it to make N2, and the oxide, somehow ammonia gets rid of it, makes water in N2, and you put ammonia in. So that's also oxidation reduction reactions. So everything you do is going to be this kind of balancing of the enthalpies So basically it's going to be Hess's law to add up the enthalpies to figure out what the reaction enthalpy is, positive or negative, and then you're going to do multiple reactions, and these enthalpies change with temperature because it's going to be the delta G that you balance out, and delta G is delta H minus T delta S. So the temperature dependent. So everything delta G is going to be linear if you plot it against temperature. I mean, you're going to have like these linear plots that show that the free energy, which I guess is this 800 number here, 200, 400, changes with temperature, right, for all these things. And this is the carbon that you say you're going to have a steel plant. So you have iron oxide. So that, I guess, let's see, the iron oxide is, let's see, iron is on here somewhere. Here, Fe plus O2 goes to FeO. So that's a straight line, right? When these things have kinks in them, that means you have the phase transition between one kind of crystal iron and another kind of crystal iron, which is another part of this chapter. So there's an enthalpy associated with phase transitions between different crystal structures because it's like a lattice energy. Like when atoms are in a lattice, they have electrostatic interactions, there's kind of steric interactions, there's a bunch of different kinds of interactions. And if it's a transition metal, depending on the coordination, so the coordination of the metal can change when it goes to different lattices. And that coordination changes the orbital structure, and that changes the interaction energy between the whatever the oxygen and the iron in the crystal. Right. So that's why you'd have like a transition in the slope of this, so that the delta H minus T delta S changes with so basically the slope of this is the S, delta S, for heat of formation between the ground state and whatever this is. So the ground state of iron would be iron solid, iron, ground state iron, metal, right? So you're trying to make Fe, and your ore is like FeO, or it could be Fe3O4. Either way, you're going to use carbon to do it. So you want to have, and these are all negative numbers because these are stable compounds, right? Like O2, Fe, O2 would be 0, and FeO and Fe3O4 are all stable compounds. So, and if you're producing a stable compound, you get a negative heat of formation. So these are all negative numbers, right? So when you're going from FeO to Fe, which is that's the operation you want to do, then you're doing this backwards, and your negative number becomes a positive number, right? So when you use a diagram like this, the thing you're trying to do, you're going to take the negative of the negative, which will give you a positive. And then the thing that you're trying to, your garbage can is going to be carbon to CO or carbon to CO2, right? And then that's also a negative number. If that's a bigger negative number than your negative number for your oxidation, which you're going to run backwards, that means the net of those two is going to be negative. That means it's a go. That means you're reducing the iron oxide to make iron. So you're taking your ore and you turn it into steel. That's the thing you want to do at a steel mill. So the question is, like, what temperature do I need to run my steel mill? Well, where those two cross, that's your magic temperature, and it's like 750 C or something like that, right? In this plot. Right. So that's one way to use this. And you can see, like, say you have copper ore, you want to turn it into copper metal. So you can see these are all industrial processes that you might run into. Right. So this is a handy dandy little plot to do that. Then also when you have a blast furnace, or whatever it is you're doing, there's also, like, you can measure the partial pressure of oxygen. So the only thing, these are all solids, right? So if you write you can write like ln of the pressure. So there's no pressure to a solid, so it's not in that equation. So if you're doing an oxidation reaction, the only pressure you have is an oxygen pressure. There's only one gas in there. So ln of that pressure times RT equals the heat of formation for the reaction, right? So the ln of the partial pressure, this gives you a delta G0 of what the atmosphere is where you are, right? So if you take the 0 for that, and then you go to this side, the red is the partial pressure of oxygen. If you draw a straight line from that point to where your partial pressure of oxygen, which if it's in a reducing atmosphere, it's going to be almost 0. Like you've consumed all the oxygen because that's why it's reducing. Like you're getting rid of the oxygen, you're making CO2, so there's no oxygen left. That's why, so it's a reducing atmosphere. That's good to make metal, like if you want to make a metal. So anyway, so you draw on this Ellingham diagram, you draw a straight, so there's a lot of plots like this, not just for this, but there's, if you do the, for like air conditioners, we have the pressure, the partial pressure and the wet bulb temperature and all that business. There's plots just like this for figuring out how air conditioners work in chemical engineering. And it's kind of the same trick. You draw a straight line from somewhere to somewhere, then it crosses the lines that you've plotted. And that's like the transition temperature where you can reduce it if you go to a higher temperature, and it oxidizes if it goes to a lower temperature. So you figure out, you measure, you have an oxygen sensor in your blast furnace, it's 10⁻16 oxygen. Then you just draw a straight line here. You can find out wherever the iron thing is, and then you know that you need, with that partial pressure oxygen, so these things running along, and you measure the part, and then you need to have a temperature over 850 for you to make steel. And if it's below 850, like say you're going from 0 to 10⁻18, so the line crosses at about 850, you got to go above 850, you're going to make iron oxide, which you already have, so nothing's going to happen. Right, so that's the idea of this diagram. It's like and then you can also do it if you're, so you can reduce with carbon, you can reduce with hydrogen, you can reduce with carbon monoxide. These are like industrial chemicals that are used for reduction reactions. You can also, I don't know if this is boring or what, but basically, like if you take silica, SiO2, say you wanted to make, so silicon can make a nice anode for a lithium ion battery, because it can hold, it's like, what is it, 14/6 lithium ions to silicon. So it's kind of like, I think you can use roughly like 5 lithiums for every silicon atom, versus carbon, graphite is a normal anode, and it's like 6 carbons to 1 lithium, 6 to 1 versus something like 15 to 4 or something. So you get a lot more lithium stored in silicon than you can in carbon. Silicon's 29 weight and carbon's 12, but basically because you're boosting it by a factor of about 20. So it doesn't matter that it's double the molar mass. Silicon is still a much better anode in terms of the amount of lithium you can cram into it. So you can make your battery for the same weight, you can have roughly 10 times the battery power. There's a couple nuances to it. I mean, one we saw, I think in here, like the cathode has to match the anode in terms of capacity, roughly. The anode can have a little bit more, but basically the cathode has to kind of match the anode. So you need to have a magic cathode that can also do 10 times the lithium. And the other problem is that the lithium expands 10 times the volume. So double or triple in size, which means it cracks. So the thing about cracks is, when you crack something, there's a critical flaw size. It's about 10 micron, right? So basically, if you have particles that are smaller than 10 micron, you can't crack it. So it can expand as much as you want if you're below the critical flaw size. Meaning if you can have nanosilicon, then you can make a battery electrode with it. But you can't you can't take silicon metal, like a silicon chip, and grind it up and make nanosilicon. One thing, it oxidizes and blows up. It just wants to bond with oxygen, so it catches on fire. For another thing, you can't grind it. There's too much energy to grind it. Like I showed in the service thing, you can only grind down to like 10 micron. That's about it. You need to go below that. So anyway, one way you can easily make silica, SiO2 nanoparticles, just by burning silica tetrachloride. Like you just torch it up, you collect it, you have bag loads of it, or train loads if you want. So what people are doing is they use magnesium so magnesium's way down here, that's good, and then silicon, Si and SiO2 is way up here. That means at almost any temperature you can reduce silica with magnesium, right, metal. So if you can get magnesium metal, you can make nanoparticle SiO2, and then you can reduce it with Mg. So sometimes you use so you can't do that with carbon, because carbon's up here somewhere. It's like carbon's a red line. So in order to reduce silica to silicon, you would need to heat it up to like 2000 degrees C with carbon. But with magnesium, you can do it at room temperature if you want. right? So it's down here. So basically that's what this is called, magnesiothermal reduction of silica to get silicon to make battery electrodes. The people are doing that. So anyway, and again, like the change in slope, like 1, 2, 3 are for different crystal structures of the thing. Actually, this is a melting point and that's a boiling point. So some kind of limit to this magnesiothermal, like you don't want to boil it. So anyway, so that's kind of this Ellingham diagram, and it's short. If you want to know more about it, there's a lot of videos online that tell you how to do this, but I'm not sure. So, all right, so you'd think like nobody would use this except someone working in a steel mill, but here, these Swiss guys are making nanoparticles, and that in their paper, they show an Ellingham diagram. They're using hydrogen in their flame. They're using that to reduce the whatever metal they want to make. So saying, and they easily get to 2000 degrees in a flame like this. So basically they can reduce a lot of things in a flame, and some things they can't, like they can't make manganese, right? And they can't make cerium, chromium, and molybdenum they can make. So some things in iron they can barely make if they get to hot flame. So something, so it's a mapping of like what they could possibly make with. So then these things, they want to use these things to make catalysts basically in the end. So you want to make them, you need a ground state metal to make a catalyst kind of sometimes. So basically they're trying to get the ground state metal so they can make nanoparticles of it in this flame. And they need to know what conditions to run it, like what hydrogen concentration do they need to get this reduction to go. So anyway, so there is a use of the, other than blast furnace, of this Ellingham diagram, you know. So it's kind of interesting that I know those people, but anyway, so this is kind of the game that people are playing. They want to make things like a spinel structure of something like let's see, spinel structure of this oh, that's pretty far down. Spinel structure of methyl ammonium lead halide, which is a perovskite for solar cells to make this kind of dye synthesized solar cell. So you can take this stuff. So this stuff absorbs just the right wavelength of visible sunlight. Right? So it can pick up, it can excite the electrons using sunlight, and then you can transfer it to titania, which is made by that flame thing. And then you can just paint this perovskite onto that, and then you can make a solar cell from that that's more efficient than a silicon solar cell, just by painting it. Right? But one problem is it says lead in it, so it's the lead halide in the perovskite structure. Basically, so anyway, so this can be easily made at room temperature from solution. It's like, how do you figure out like what? So how do you figure out like which of the kind of reaction is going to work for things like that? So that perovskite, when people talk about perovskite solar cells, that's what they're talking about, is that material. There's other kinds of perovskites that exist, right? So anyway, so these kind of complicated crystal structures are basically usually involving some kind of transition metal. So it can go through different transition states, and then different d orbital structures. And there's energies associated with those different structures. So you need to be able to kind of add up the energy in the thing, right? So it can be kind of a somewhat complicated process, right? And usually there's an organic material in it, so it's like an organometallic kind of system that you're dealing with. And then that's going to be used for whatever sensor. It's going to be used for like collecting light, catalysis, maybe biomedical, something or other, you know. So basically there's a lot of things that this kind of structure can be used for, right? But you need to be able to figure out this kind of adding up the Hess's law of all the enthalpies of formation in order to be able to make the things. That's the idea. So anyway, so the idea is just like you have the ground state magnesium that you got from this table somewhere, and then ground state silicon, and then ground state oxygen, and then you have the energy for this olivine magnesium silicate that you can make, right? And you just subtract these from that, and you can get the energy of formation for that Hess's law kind of thing. right? So that's kind of one part of this chapter is like calculating these energies for different kind of states of material. And again, like it has laws, like it doesn't matter what route you take to get to the structure, as long as you have the energy of the formation of that, then you can like how do you go from liquid to beta? You just subtract those two and you can get the energy, the enthalpy of that operation, right? So then in the chapter he goes through some like rules of the game, like so titania is a transition metal and it can go through different crystalline forms, many different crystal forms. So here's some of the crystal forms for titania. And then basically this is just a plot of the heats of formation, and there's kind of a minimum in it. So basically you can map out the heats of formation. I guess the kind of want to know what's the rules of the game here. So each crystal is going to have so one rule of the game is this electronegativity thing, right? So you have like chlorine's the most electronegative, and then whatever things are down here are the least electronegative, and it more or less goes across the periodic table like that. So if you have something like a low electronegativity and a high electronegativity bonding, that makes a strong ionic bond, right? CSF would be like the least possible, cesium would be like the least possible electronegativity, and chlorine's the highest. So it makes the most ionic bond that you can get. And then when the two things approach each other, right? If it's a high electronegativity, like you have a lot of electrons, basically, then it becomes a covalent bond. And if it's low electronegativity, it becomes a magnetic bond. So you can kind of see like copper and aluminum are like lower electronegativity, metallic, and then B and boron and nitrogen are higher. So the things that are close on the periodic table form non-ionic bonds, but if they're kind of to the left, they form metallic, and to the right, they form covalent. That's more or less how this works, right? So, and there's a continuum. There isn't like, so some things are kind of have some features of all three, right? So it isn't like definitively metallic, definitively covalent. There's a continuum between these things, right? So anyway, so that affects the energy of the bonds in the system. So how are you going to make like NaCl? Like, so you start with Cl2 gas, and then so you follow Hess's law, then you have to somehow get NaCl from it. So you have a gas and you have a metal, a ground state metal. So in order to take the ground state metal, so you're gonna end up with gases that you mix, ionic gases, and then they're going to be formed into a crystal. And that the change from the ionic gases to the crystal is called the lattice energy. And that's going to have components like electrostatic, van der Waals. Each of these terms will have a bunch of components to it. Like if you want to build this crystal, right? So this is a simple like NaCl, but it could be you're making some perovskite thing, right? This will be the same rules. You have the stuff you start with and the heat of formation, enthalpy of formation for that stuff, right? So if you start with a solid, you have to make it into a gas. And if you have the gas, you have to make it into an ion. And if you have the gas, then you want to dissociate it into a non-charged gas, and then you have to do an electron gain to make it into a negative ion. It's kind of lose an electron and gain an electron. So ionization is losing, electron gain, something people don't usually talk about much. It's a hypothetical step in this thing, that's why. And this is actually something that happens. Right. So in other words, if you have chlorine gas and you make an ion, that's kind of one step. And this isn't. This is actually, you can make a vapor, a metal vapor of sodium. Then you can ionize it separately. Right. So anyway, so for thought processes, everything's broken into steps here. And then if you add those heats up, you end up with this heat of formation. That's kind of the idea of it. So you have basically break the reaction into these steps, and each one has a heat of formation. Then the heat of formation is going to be this lattice enthalpy. So the lattice enthalpy is usually written that you break apart the lattice into the components. So in the equation, in the book at least, it's a negative term here, like the negative of this positive thing to break apart the lattice ends up being a negative addition, and the other things cost energy. So this one adds energy. This one drives your process, and these detract from the process. That's mostly the idea of this thing. So anyway, so the lattice part has all these components to it, right? So electrostatic, which is Coulomb's law, repulsive and dispersive is a 612 potential, and then polarization and crystal field. So if you look at simulations of this stuff, so this is kind of written for like computer simulations of the growth of phases, right? So it's broken apart in this way because these will be like terms in your equation of determining like if a crystal is going to form. So these two are coupled together, 612 potential, polarization and crystal field are terms that you throw in, and the electrostatic is Coulomb's law. So you have the Coulomb's law as a charge divided by the distance, and then all right, so each of these terms has, so if you have your lattice, you have nearest neighbors, and you have second nearest neighbors and third nearest neighbors. So like in NaCl, it's like a face center cubic with a Cl on the side, in the middle of the sides. So the first nearest neighbor is NaCl, so that's going to be a negative. That's going to help your situation. So in terms of the lattice, because this is a negative term here, so it's positive here, right? Because it'll become negative when you make it negative. It's like this is like the breakup of the lattice energy, right? And then it's the same form for all these, except that you have six of these within the unit cell. You have 6 of these NaCl bonds. Then there's 12 of the Na bonds, and then there's going to be 8 of the third nearest neighbor, which is NaCl again. Should be like the cross, kind of a cross term or something. Right, so anyway, so you add those up, but so basically you're going to have like the charge of an electron, the distance, and then this geometric factor that shows up. So that thing's called the Maudling constant, and it'll be just a number, right? So basically this electrostatic, and again, this is more or less for computer simulation of the growth of the crystals. You're going to calculate electrostatic. So you have this Maudling constant you can look up for a NaCl type crystal structure, and just put in whatever your lattice spacing is, this Rmx, like the lattice spacing from diffraction. And you can get this electrostatic interaction, like the first term of the lattice energy. Then the repulsion dispersion is basically the 612. Let's see. What is this business? The 612 potentials of the repulsion dispersion thing. So the 12 term is kind of made up, right? So, and you can replace it with an exponential for ceramics if you want. It's named Buckingham potential, they call that. The six comes out of the van der Waals potential, which is a calculated number. So the 6 part of the 612 is an actual number, an actual function that you can calculate theoretically, and 12 part is just something that works okay. So it's kind of like a hardcore potential. And this is the attractive thing at long distances. So anyway, so that thing gives you that kind of like a dip, like a valley, and then a curve. Like you have the potential, and it's going to be like kind of like a U-shaped thing. And the minimum of it, you can find the average separation distance between the atoms due to this repulsion and traction. So anyway, that average distance is usually a number in your computer simulation. So you usually have that, this is parameterized in terms of that number. Then so the other parts of that, so the crystal field and the polarization, these things don't have functions. So these are just like numbers. So basically these things are going to come depending on what the materials are that are in the lattice. Like what, if it's a transition metal, then you need to worry about the d orbital condition, like if it's split by the Cl and the NaCl. So those are more complicated to deal with. This just shows as a function of so this is a sodium salts, and then the most electronegative to the least electronegative. So again, positive, because it's going to be negative in the equation, positive means a strong crystal. So the more electronegative has a stronger crystal. This is the lattice enthalpy, right? The sum of all those things. And then this is for iodine, and then looking across the you're looking down the kind of down the alkali metal track. Right? So getting to be less electronegative as you go that way. So the more electronegative has a stronger crystal, stronger lattice enthalpy. And then these are the other parts of forming the crystal, right? So dissociation, electron gain are the other parts here. What it is. So that's like dissociation, electron gain are these two parts that go with the halide, right? So basically those don't change with electronegativity. Right, so the lattice energy is changing. Association electron gain is pretty much flat. And then the ionization and atomization is higher for it's higher for more for lower, higher electron negative alkali metals, right? So this and so this drops and that drops, but this is negative, so this thing counteracts that. Or when you go across the alkali metals, like this thing counteracts that. So when you go across alkali metals, the sum of those two gives you like a flat. But the sum of the two, because this drops and this just goes flat. So as you go across the halides, to more electronegative is going to have a stronger total enthalpy of formation. Change in the halide has an effect, change in the alkali metal doesn't. That's the idea. And the reason for it is because this ionization and atomization depends on the alkali metal, whereas the halides don't change anything for dissociation and electron gain. Because you're adding up all these things. You're adding all these things together to get the final heat of formation. So if it's the alkali metal you're changing, these two things counteract that thing. And if it's the metal you're changing, these two things do nothing and this thing changes. So changing the, I said that backwards, but changing the halide changes the overall energy of formation. This shows like changing the alkali metal doesn't do anything for the heat of formation. Changing the halide does. Again, it's because the halides don't have any change with electron gain and dissociation, whereas the alkali metals do for ionization and atomization. So anyway, so that's some kind of thing that's interesting, I guess. I'm not sure how important, but basically it's one of the things that are there. And then it's in the book anyway. So this is what is this? Going across the this is going across the all right, so he's got the alkali metals somewhere here, and then he's got the not the alkali, but the second group 2 metals, right? And then he compares that with group 12, like here. So he says that because the electron cloud of the group 12, like the zinc, cadmium, mercury, interferes with the what, the ionization and the so because that somehow that interferes with this flat curve, and then these things change and this one doesn't, right? That's, or it goes the other way or something. It's something to do with the electrons, and the 12 extra electrons shield the nucleus. I didn't really get what he's talking about here, but basically there's a difference between the group 2 metals and group 12 metals, and you go across the halides. And one increases heat of formation, the other one drops. So, and whatever the argument is, it's something to do with the electron cloud is larger in the 12 group. Right, so that brings us to this business. So there's a pretty good, so I don't know if you guys have done like a lot of this transition metal business. Let me just get out of this and go back over here. So enthalpy formation. So there's two sources here. If you haven't done this one is pretty easy. Like you can just read through this, and it goes through the entire thing in one page, right? About how this whole thing works with the d orbitals and everything. And then the other source for this that's pretty good is like it turns out like this, you'll see like over and over again. So this Hausgraf inorganic chemistry book, right? I think it's like chapter way down, like chapter 10 or something. This is like the Bible, recent Bible for this, for inorganic chemistry, which is kind of what the d orbital stuff is. So he's got somewhere in here. Oh, let's see. Look at the shorter table of contents. Blah, blah, blah. D block metal, blah, 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 661. Wherever that is. Let me just go down there. Anyway, he's got there's a whole like series of chapters about the d orbitals for transition metals, which ends up being like the main kind of a major thing for these, especially for the metal organic compounds. 61A. So this is D block metal chemistry, right? So it's chemistry, and you see like the same kind of plots, that are in the book. So basically, the book's taking a lot of the stuff from this book, and also the stuff in this web page is from that book too. So everyone uses that book. So basically, you want to know what's going on beyond my minimal knowledge of this area. This book is the place to go. It's page 661, and he'll go through like every possible. If you enjoy looking at this is a place to go. So, yeah, so there's two kind of sources. There's some other things in here on this. There's this Cotton book, which is a book, when I was an undergrad, people used this Cotton book, and I have a copy of it. I'm not sure I ever got much out of it. That's like also the Bible. Before Housecroft, that was the Bible for this kind of stuff, inorganic chemistry, bonding and things. So anyway, there's those three things. I guess I'd recommend like looking at that splitting of transition metal orbital energies webpage. That's pretty useful to look at. So the transition metals like in the middle, right? So it's kind of like the blue ones here. So basically they can have different oxidation states. That's the idea. So what happens when you go through this? Well, they're going to form they can form these different orbital structures, right? So you have anyway, so these have to do with the let's see, someplace I have this set up better than that. Here. So So this is the orbital, like the Aufbau principal electron orbitals, right? So you have like 1s and then 2s, 2p, 3s, 3p, 3d. So iron would be like 3d with one electron in every. So each of these orbitals has a certain number of electrons in it. It's like 2 is a normal thing. They can be paired or unpaired. Right, so you have 2, and then 6 is 8. And then the p is another 6 that gives you 14. And then 16, and then 22. And then to get to iron, which is 26, you need 5 d orbitals, 3 d orbitals, right? And the d orbitals are the ones you're interested in. So iron has like 5 3d orbitals. It's usually the one you want to look at. It's like the standard transition metal thing to look at because it's so common and whatever. So, but all these other metals can also be done that way. It's like if you look at like manganese, it's going to have like 4, and then cobalt will have 6. It means with cobalt, with iron, you can fill all 5 of these D structures, right? X, Y, X, Z, Y, Z, X squared minus Y squared, Z squared. You can fill them with one electron. And the idea is you want to have like paired electrons. If you have independent electrons and you have a paramagnetic, so it's a magnet. And if you have all paired electrons, it's a diamagnetic, because it's got like this kind of magnetism up and down thing, right? So it could cancel, but there's no magnetism, or it can be that one's bigger than the other. Anyway, so that's kind of the idea of this d orbital thing. So all this region transition metals have this kind of scenario, and the oxidation state is going to change like the arrangement of these the orbitals of the thing, of the atom, right? And that, so the orbitals of the atom change with the ligands that are in the crystal. Like with perovskite, you have three. You have a transition metal, then you have like a anion of some kind. So it'd be that ammonium anion if it's the perovskite for crystals, for solar cells. And then the lead would be the transition metal. And then you have something else like cobalt or something in there. There's three components to it. So the anion can be arranged around the metal, the transition metal, either 6, which gives you an octahedron. So the 6 corners of this thing, there's 8 sides. Like the top has 4 sides, the bottom has 4 sides, so it's 8 sides. So it's an octahedron, even though there's 6 things around it, right? Could be a tetrahedron that's got like 3 things, or it can be a square. It's kind of like 3 options for the way the anion can be arranged around the metal, the transition metal in the middle. And depending on how that's arranged, it's going to split up these electrons in the orbitals differently. And each of these orbitals, so if you start with the metal cation alone, all these orbitals have the same energy. So it's not distinguishable between them. But as the anion approaches it splits these d orbitals into different energies. You have these octagonal energy difference between these X, Y, X, Z, Y, Z orbitals and these squared orbitals, right? And that means that can absorb light, for one thing. So that means that if you change the distribution of the electrons in these, the color of the thing changes, for one thing. It can make it, that change in energy can make it catalytic, like titania, anatase titania is catalytic, and rutile titania isn't. So this kind of orbital splitting can provide the energy necessary to do like oxidation reduction reactions. So it can be a catalyst for oxidation reduction because I guess when the oxygen approaches it, something happens that makes it catalytic, right? So, okay, so that's kind of the idea. So anyway, so these are like the possible orbital arrangements. And then for the d orbitals, let's see. So there's a picture of these guys here somewhere here. So basically these are the pictures. So they're set up so the metal atom's in the middle, and these are the electron clouds around it in the d orbital. And there's also s and p orbitals in the thing, right? So we're just looking only at the d orbitals, which are the lowest energy, since they're kind of in the outside of the atom, right? So the ones that interact, the lower energy ones are the ones that interact. So basically, this x squared, y squared, so they're just different shapes. So depending on if you stick this metal into a octahedral crystal, then some of these orbitals will interact with the anions more than others, right? So they're showing the anions here, just showing an octahedral ligand, showing like how the anions, which are the little grayish black negative signs, interact with these orbitals more, some of the orbitals, and less with other of the orbitals, right? So basically, like here, the xy orbitals are squeezed right between all the octahedral, and so are the xz, and so are the yz. That's why they're lower energy. Like the electron don't interact with the anions. Whereas here, like the z squared, the electrons are directly in the way of the anion. That means that's a high energy situation. Same way here, the side anions are like directly penetrating through the x squared, y squared orbitals. So it's a geometric effect, right? In other words, the geometry of these orbitals makes some of the orbitals have a different energy than others of the orbitals. And that means an electron can go from one orbital to another. There's an energy between the transition of that, right? So depending on how these ligands, and in these crystal structures, it can transform from octahedral to tetrahedral. You can have that transformation, and then this whole scheme of the energies changes. So you can have like energy that involved in like a chemical reaction. That energy difference can be involved in some catalytic reaction or something, right? So that's kind of roughly my understanding of what's going on here. This is just showing that the bare one is at this energy level, and then if you start adding the anions, then the energy goes up, and then when they approach into an octahedral form, it splits. The squared ones have a higher energy because they're close to where the anions are. And there's the interaction with the nucleus has to go through those clouds, and that makes it a higher energy. Then you have this delta energy of the octahedral is like the main. So you talk about octahedral and tetrahedral sites in the perovskite crystal for the two metals, right? And the two transition metals, and it's going to affect these orbital energies. And then this is all in terms of the enthalpy of formation. This all adds into the energy of the crystal to form the crystal. So that's that business. Let's see what we need to know. This is just showing the same kind of dependencies on the periodic table position, like the electronegativity, and then the octahedral energy. So you measure this octahedral energy by doing a UV spectroscopy. You get a peak. So you shoot light through, it absorbs energy at this octahedral energy, and then basically you get a peak in the absorption band. And then from that absorption band, you can go back and calculate what this thing is for the octahedral. And there's a direct relationship between the octahedral and the tetrahedral. So once you measure the octahedral, you can calculate the others. You can calculate the other d orbital splitting energies. So anyway, so let me get rid of this thing. This is from that web page. It just goes. That's linked on my web page, but it goes through each of the. Goes through octahedral, tetrahedral. See, octahedral shows the kind of how the anions and the electron clouds interact, and then tetrahedral also shows how they interact. Tetrahedral here. This is octahedral. The tetrahedral is down here. actually, it doesn't show how they interact, but it shows that I guess it compares the octahedral energy to the tetrahedral energy, and the tetrahedral is 0.44, the octahedral. This you can work out somehow from this, but so that's kind of the idea. And then the square planar arrangement, and that energy is also related to octahedral. So this is square planar is higher than octahedral and higher than the tetrahedral, and the tetrahedral is smaller than the octahedral energy between the bands of the splitting of the d orbitals. This is just showing, like, if you go through a transition from metal and octahedral, and then how you transition to a square planar through these splittings of the d orbitals. So that which one you get depends on how strong the ligand is. I guess that's the point of this picture. So if you go into like fluorine would be like the strongest ligand, then you would get to these higher energies kind of splittings. And then if you have these ammonium things, you get like octahedral that have a weaker ligand field strength, like electronegativity, basically. So what else is in here? So this is from that web page, and it just goes through. Well, he goes through a series of kind of problems. It might be good to look at some of them, but so FeCl6 -3 anion, right? Depending on the number of d electrons for Fe, so that's 5 because you have this. Basically, you have, if you add this up, you'll end up with 8 for 3d, and 8 minus, it's got -3, so it gives you 5. So it's 5. If you should go through adding up how many electrons until you get to 3d for 26 for iron, you find out that d would have 8 electrons in it. So it'd be this, and then if you have a -3 anion, you have to remove 3 electrons from that, and you end up with 5. And that would fill the 5 possible d orbitals if unpaired, right? So if it was iron, not 3, there'd be 3 more, and they would be, the ground states would be 2 electrons in each one, and you'd have 2 unpaired up here. And that's also magnetic, paramagnetic, right? But this is paramagnetic because they don't pair up. So because chlorine is a strong electronegative, or let's see, chlorine is a weak electronegative on the periodic table, right? So chlorine. See, he says a weak ligand here. Turn the state of Fe plus 3, 5d electrons. Fe, sketch the d orbital energy. So determine the geometry of the ion octahedral, which means the energy splitting should look like that. It's octahedral because there's 6 ligands. So you have, per octahedral, you have 6 points, and then there's 8 sides. So there's 4 on the top, 4 on the bottom. So anyway, you determine it's octahedral because there's 6 chlorines in it. And then if it's octahedral, that's the way the electrons are going to be arranged. You have just this octahedral energy. Then determine whether the ligand induces strong or weak from the spectrochemical series, which I didn't mention. So there's a, let's see. The spectrochemical series. Let me just get, spectrochemical series are in this slide somewhere, but I can just get it from the web page, I think. I'll figure out how to do that. The web seems to be going slowly here. This is actually just going through this web page. So Fe63 spectrochemical series right here. This is the series, the weakest to the strongest, and Cl is in the weakest part. I'm not sure why So it doesn't go with electronegativity, because so fluorine's the most electronegative, chlorine's less electronegative, iodine's less. So it kind of goes in that sequence, but then it's a sequence of all these possible ligands that you could have. So the weak ones allow you to fill all the D's with one electron. The strong ones, then the D's would be, then the electrons pair up. So if you have like cyan anion, then basically the 5 would be paired two on the bottom, 2 pairs on the bottom, and then 1 free electron. If it was Cn instead of Cl, the distribution of these things would be, if it was Cn instead of, let's see, then it would be like 2, 2, and then 1. So it'd still be paramagnetic because you have an unpaired electron. But basically, these two would be down here with Cn, and with Cl, it's set up like this. That's why he says that's how it would go, because Cl's to the left of that series, weak ligand. So they fill all orbitals being paired. And then what's the next? Because distributing electrons, list the number of lone electrons. There's 5 lone electrons. Label it as paramagnetic. So it's paramagnetic because you have 3 electrons, 5 unpaired electrons, paramagnetic. So strongly paramagnetic because you have 5 of them. Whereas you can have as many as you could possibly have for an or a octahedral D splitting. So it's as paramagnetic as it gets. That's the idea of this. So anyway, so that's kind of one of the things here. He's got a series of questions he goes through. So this is another one. So he's got so he runs the UV spectrum. He finds that there's a peak at 545 nanometers, right? And he wants to know, and it's a tetrahedral. It's a tetrahedral D splitting, right? So he knows it's tetrahedral. He knows he has that absorption. So then he wants to know what would the octahedral be? And it's like 0.44 relates octahedral to tetrahedral. Right, so at some point he's going to use 0.44 to get the octahedral from the tetrahedral. He needs to calculate this tetrahedral energy first. So he gets that from the energy equals hc over lambda, is the Planck's law, right, to get the energy from the wavelength of radiation. And then h is Planck's constant, c is the speed of light, and then he has that 545 nanometer. If he converts to meters, he's got meters per second, and then he gets joules. Gets joules from that. The seconds cancel out. So he gets that many joules. And then that is for joules for 10 to the minus 19. So that's for 1 atom. That's energy for 1 atom because why? What tells you it's 1 atom? It's the energy for 1 atom. Because it's such a small number, it's for 1 atom. It's a pretty small number, 10 to the minus 19, right? So you'd multiply that by Avogadro's number to get the energy per mole, right? So per mole of whatever this is. He never says what that is. Anyway, so that's just how you get those D-splitting energies. Let me see what else. Why didn't I include any of these other ones? Petrochemical series. That's not what I want. Let's see, I want to move this over. There. I want to go back. Example 2, that's exactly that example. There's a video of a guy from somewhere talking about this stuff. Then it's just sketch the d orbital energy levels for this list. Yeah, I see why I didn't do it. So anyway, you can go through those if you want, and that's it. So yeah, all right, that's why I didn't include those, because that would be kind of painful to do. So anyway, why don't we skip it too? That's why I didn't do it. Anyway, so that's part of the chapter here. Hopefully that's, I mean, I'm not an expert on d orbitals and things, but basically, hopefully that gives you enough. And if you want more, there's that web page and there's like that book. The book will definitely give you everything you need to know. So I'm going to leave that there. So let me get rid of this again. So so yeah, this is called the crystal field effect. So basically, depending on the d orbital arrangement, right, it's going to change the energy of the crystal. It's going to change the lattice energy. So let me just. So this is just listing like what can affect this lattice energy, oxidation state, size of the metal, types of ligand. That's, oh, there's the chemical series for the strength of the ligand. And then this is just showing that business about d orbital splitting, changing the lattice energy, heat of formation, and then so let's see, this is just, I think this is just electronegativity, right? Going up to this is, oh, this is across transition metals, increasing electronegativity, I think. Well, it's adding electrons to the d orbital. So ionization enthalpy of the first series. Atomization component, lattice component. They've broken down the enthalpy of formation into the ionization for the same group, the lattice, and then the atomization. And he's saying that somehow the d orbital splittings when you get to magnesium reduces this, I guess. I'm not sure why there's circles, drive lattice. Yeah, I don't remember exactly. Basically, he's just kind of saying there's trends in this that match up with the de-spacing thing. Oh, what else do I want to talk about here? Yeah, there's also this issue of acid base. This also like you can write the free energy, like the Hildebrandt interaction parameter for mixing two materials in terms of acid and base. There's a whole set of rules for that. We can calculate the Hildebrandt by the acidity and basicity of the different components that are going in. Right. And this mimics that for heat of formation for crystals. So he's saying like basic and acidic components will give you a higher energy. When you have more basic and more acidic combined gives a higher like heat of formation. That's the idea. So basically this is showing like, kind of how that works. I mean, just showing trends that match that up. BAO is most basic. Yes, magnesium is least basic. So you get a higher energy of formation with barium than with magnesium. And sulfate's more acidic than alumina. So that's kind of the idea here, that we could use that acid base idea to predict heats of formation. Yeah, and then there's issues about, so things have to fit into the lattice. So if you have lattice strain, it makes the crystals less stable. That's the main idea. This is just showing the perovskite structure. So it's a simple cubic structure, and then you have kind of face-centered locations and body-centered location, right? So basically the transition metals in the middle, and this the corners of this. Let's see, the octahedral anion of the gray things, and then another metal is the corners of this thing. That's how it works. So you have two metals and an anion set up, right? So you have an octahedral site, and I think these are tetrahedral in the corners. That's the way this thing works. So you can draw it that way. That's the simplest way to look at it. You can draw it that way. And you can draw it in terms of these kind of diamonds that show the octahedral sites like that, right? So there's different ways to draw this thing. Anyway, so it's just showing the energy formation across different groups and perovskite structures. I don't remember exactly what else is in this. So this thing, this metal organic thing, the papers got something to do with the zeolite business. So this isn't really crystal structure. This thing starts with like a block copolymer as a lattice. I mean, there's natural form zeolites and there's synthetic zeolites. And synthetic zeolites are going to have a block copolymer, and then you're gonna fill in one of the phases with tetraethyl orthosilicate or some other silica precursor, and then condense that and make silica, and then remove the organic component of the thing and end up with pores. Remove the block copolymer organic part, pyrolyze it, and end up with a pore structure that's templated onto the block copolymer structure. This, I mean, so this is showing like the silica tetrahedra making kind of a lattice, and then there's these holes. So it's trying to show like micro porosity and macro porosity, or meso and micro porosity in the structure. The block copolymer is making these big holes, and the little holes are being made by the silica formation. Right, so you can have like two porosity structures, and that's going to be like a lattice that you put a transition metals onto so that you can get catalysis from it. So it's basically a scaffolding. Or it could be, or if you crystallize not just silica, but if you crystallize some other crystal in that, like a perovskite, then that could be actually catalytic itself, like the framework can be catalytic. So anyway, so I'll probably like go through this. Let's see, we got 10 minutes. Huh? I'll have to go through this next time. I haven't really gone through this yet recently. Yeah, this enthalpy of formation, there's one part about polymers in this, because there's nothing in this about polymers except that the block of polymers uses templates. But there's this idea of, so polymers are going to be a chain molecule, and then they carbon you can rotate about that bond, right? So you can see if I have a plot. So if you rotate around that bond, the chain, like say this methyl group is the chain, so those two can be next to each other, right? Or they can be kind of in this notch between. So they can be para, which would be when they're opposite. How's the opposite here? This would be a para, kind of a para, like when the chain group and the other chain group are opposite each other. Oh, here, it's down here. So there's para, so they're opposite. So that's the lowest energy. And then you can get to these energies where they're gauche plus and gauche minus, where you have a higher energy, right? So you have like low energy, high energy, and when the chain spins around, they're going to go through these barriers, like energy barriers. So you have a delta energy between this and that, right? So if you think about like the probability going through that hop, you use a Boltzmann probability, it's going to be that energy, that barrier divided by kT exponential to give you the probability of kind of hopping between one state and the other, the lowest energy and these kind of metastable, right? And then if you want to add up all the energies, you get this partition function. So if you add up all the energies of the system, all those probabilities, then that should sum to this Z. Right, so that's called the partition function for the structure. It's like the energy, the total probability for the whole system, right? And the probability of one state, of having one angle, rotational angle between the things, it's going to be the energy of the probability of that one state normalized by this partition function, the sum of all the probabilities. That gives you the probability that you're going to get one state of the thing, right? And that one state is going to have an energy, like it's going to be an energy on this plot. Right, so you can calculate the kind of the conformational state of a chain, like how each of these units is spun around. Like what's the natural state for that chain to be in using this kind of energy of formation analysis kind of thing. It's kind of an energy of formation. It's called a conformational enthalpy for the chain. And so, that was kind of Florey's. That's what Florey was cited for the Nobel Prize, was figuring out how to calculate the energy of a chain, that Palmer chain, using this kind of idea that you have a Boltzmann probability for each of these rotations. There's a partition function to sum up all those, and you get probability for each of the conformations. And then from that probability, you can predict what the energy, kind of minimize the energy for the whole chain and find the structure of the chain from that. That's called the rotational isomeric state model, RISM. But anyway, yeah, so it turns out the free energy for the system is the log of that sum of the probabilities. We'll talk about that later for heat capacity, but basically that's a standard thermal thing. So it's the sum of these probabilities. So basically the sum of the probabilities is going to be exponential of the free energy for the chain divided by KT. In other words, a Boltzmann. So the sum of probabilities is the total energy of the chain by KT, exponential, Boltzmann kind of thing. And then, you can get the entropy of the chain and the free energy of the chain from that sum of those energies. And then from that, you can get the internal energy of the chain, and from that you can calculate the heat capacity and things of the chain, kind of going through that routine. So anyway, that ends up being a lot of math, I guess, to do that. But anyway, that's kind of there's a web page also on this business. This isn't in the book, but since there's nothing on polymers in this section, I thought I'd stuff that in. But let's see. Let me here. There's a bunch of things on like there's RISM, and then there's two things about RISM. There's a polymer physics. These are all like web pages. I don't know. I guess that's about it for today. And I don't really have much more. I'll go through in detail the like on Thursday, the business about whatever I skipped at the end of this business about the D splittings and things. And then I'll go through that homework too on Thursday. Maybe I'll go through the last homework and also that new one. Should have time to do that. So that's about it for today, I think. Unless there's questions or anything. No.